so much for having me. It's nice to be back at Naval Medical Center to the extent that anyone is back. Welcome to the surreal world. So I was asked to do grand rounds sort of at last minute, and it was mentioned there, I've been trying to put some of my lectures up online anyway, so this was a great opportunity to kill two birds with one stone, to be here and to talk about one of my absolute favorite topics, which I hope you will find somewhat useful, or at least mildly interesting, or at least can use as a sleep aid later if you need one, which is the philosophy of science for medical providers, or really for anyone. Why the philosophy of science really applies to so many aspects of everyday life, and learning that you probably never actually learned any science in school. And I'll explain that later, because why that can seem strange that you probably never actually learned any science in school. So, but first of all, being the narcissist that I am, I'm going to talk about me and why I'm introducing this topic. So I spent a lot of time in school, way too many years. A lot of people wasted their youth on, partying or drugs. I wasted my youth on useless education that I don't use except for the occasional lecture like this. So, but I always wanted to be a scientist. Somewhere, my mother, as far as I can tell, has kept everything in existence from the history of time, but I've never found the actual drawing that I made when I was in about kindergarten or first grade, where I remember making a drawing talking about the fact that I wanted to be a scientist. This is not my drawing. This is one that I just Googled, and one of the things I found very encouraging in Googling it, by the way, when I Googled kids' drawings of scientists, is actually about the first 20 ones that show up are all pictures of women. So the world is getting to be a better place despite COVID and all the craziness in the world, I think. Whatever this kid drew has a cool robot in it. Mine didn't. But the point is that I was really inspired by science at an early age. But I probably had an incorrect idea of this. This is a quote that I love by a professor at Boston University that I think sums up a lot of things. As an adolescent, I aspired to lasting fame. I craved factual certainty, and I thirsted for a meaningful vision of human life. So I became a scientist. This is like becoming an archbishop so you can meet girls. It doesn't really work. A lot of people's vision of what a scientist is, it turns out to not be entirely correct. Now, maybe you're much better off and were much wiser than I was starting at an age. And I encourage you to participate and step in here. I really wish I was able to give this in front of a live audience. I think those are much better. We all talk together about that. I don't by any means claim to be the smartest person, even in the virtual room. So please speak up and talk about your experiences and things. And there will be some sort of call and response questions as we go through. But at least for me, the sense of where I came to this was one of the first books that I was taught as a kid, that my parents read to me when I was very small, was The Once and Future King, which is a book about King Arthur. As a side note, I was going to include a video here, but for various reasons, videos didn't work quite right, of Monty Python and the Holy Grail and the Is She a Witch scene, which is actually a beautiful explanation of the scientific method and of inductive reasoning, and plus is just hilarious if you haven't seen it. But for me, my association with King Arthur and fantasy and science came from the fact that in this book, Merlin describes himself in the book as a scientist. And I think for a lot of kids, definitely for me, but a lot of science fiction and fantasy fans and people got inspired, there seems to be this aspect in nerd culture where that shows up. There is a love of science by virtue of the magic of it, about what it produces. And there's a quote by Arthur C. Clarke, the science fiction writer, but actually was a pretty impressive scientist in his own right in terms of developing some things for satellite communication. Talked about that any sufficiently advanced technology is indistinguishable from magic. The wizard can create the fireball, but so can flamethrower. All good things if you're a nerd kid getting butt womped as a kid and wish you could throw fireballs at people. You think, well, I can't do that. Maybe one day I can make my enemies spontaneously disappear. So there was this sense that science is wizardry. But unfortunately, as you go along, if you actually do the work of science, you'll discover it's not magic. Not in the sense that you can just create things by any stream of the imagination. We see the wonders, the results of science down the road, and we often miss just how messy the whole process is that goes into it. Many of us have maybe heard this quote from Thomas Edison, and what you think of him as a scientist is a separate issue. He did kind of really rely on a lot of workers below him, which is also true in science. But in real life, science is tedious, frustrating, fraught with many more failures than successes. As Edison said, I have not failed. I have just found 10,000 ways that won't work, which sounds very inspirational until you're the actual person in the trench failing 10,000 times to get to something that is going to be a lot less lucrative or lasting in time than developing the light bulb. But as you go along, at least for me, but I think also, again, for a lot of people, you learn to fall in love with science again, despite the arduousness of it, because despite all its difficulties, it's kind of like that quote by Winston Churchill about democracy, which is that it's the worst system in the world except for all the others. And it really has been the light that has led us out of darkness. And I'm going to show some graphs a little later about human development and how the scientific revolution really changed the world in ways that nothing else had before. And a lot of it revolves around light, by the way. So not just figuratively, but literally our understanding of light has led us to so many philosophical and thought ideas that helped us in so many other areas. So if I couldn't be a wizard, I wanted to be probably Carl Sagan. This was my saint growing up. I fell in love with Cosmos, the TV show, and then later his books. And I'm going to rely on some really brilliant things that he put together to summarize some ideas about the philosophy of science and what he called rules for baloney detection. And in reality, I don't think I can be Carl Sagan. He was infinitely more poetic than me. Neil deGrasse Tyson, no, still probably not. Bill Nye, no. Maybe Bob Newhart, at least he was a psychiatrist in there. No, but at least I'm the guy giving the lecture here today. And science did offer me the great opportunity for this. So beyond its use as a thought process, which is in its essence what it really is, it has offered me some wonderful opportunities being here today, but also to travel around the world, to present at some wonderful conferences, to really engage with some of the most intelligent and amazing people in the world. So it has been a fulfilling experience to be a part of that process. But even if you never want to become a scientist, you don't like presenting at conferences, you don't like being the first person to discover even something very small, most of us understand that science is in the news. It impacts us on a pretty big daily basis. It seems to have become quite political recently, but it always has been. The front page of the New York Times, of course, in the year that I was born, I was named my middle name after Neil Armstrong because this scientific achievement, man landing on the moon, was so impactful that it impacted society in ways that, it's hard to argue that maybe anything has in my lifetime since then. But it's still clearly impacting us on a daily basis in all kinds of levels. And there are a number of these things where, again, the interpretation that you get can be quite contradictory. You'll get, from one side of the news spectrum, one piece of information, and another side, another. And oftentimes, both sides will be saying, just rely on the scientists. But do you understand the science yourself? For climate change, I think was the one recently that has really come up where both sides claim the scientists are on my side. But no one seems to be willing to go through the steps to understand the process of why particular scientists believe particular things and how you sort through the information to make that decision for yourself. And it's obviously not just that. Vaccines, I think, as medical providers, something that really we see a huge impact of in terms of how we communicate science, how we think about science, that there are people who clearly don't believe that vaccines are effective, or that they're dangerous, or read a particular study, in fact, one particular study that was published and then retracted in terms of it causing autism, and why most of us don't believe that study, but getting into the weeds of that and why literally thousands of other ones afterwards have refuted that information. And there are lots of conspiracy theories that tie into this at all kinds of levels in terms of scientific understanding. Big one is in terms of just the engineering of something about the Twin Towers at 9/11. There's this thing called AE 9/11 Truth, which is posted online, which claims to have, quote, 2,500 architects, engineers, and students who call for a new investigation and will point out that it was, quote, impossible that planes brought down the towers. Of course, the most obvious empirical evidence for how we know that planes brought down the towers is that we all saw planes hit the towers and then the towers fall. But beyond that, in terms of the science and the structural engineering of this, you can hear things like this and think, oh, well, maybe a lot of scientists believe that and not realize, okay, yeah, there may be 2,500 architects or engineers who've said that, but there are over 150,000 just people in the American Architectural Society. So that's a pretty small fraction. But nevertheless, these sort of things can make the news. And hopefully we're not just depending on a vote by numbers, but on understanding the science. And where, of course, all of this has come together is all the levels of conspiracy theory and the fact that the science is new and coming out every day. Even for someone who is very good at interpreting science, you may realize that, oh, you didn't see this new thing that came out yesterday. And there's these new studies over here and this new study over here, and the meta-analysis has not been written yet. So how do you add this stuff together? How do you determine what you should do for yourself, for your patients, your beliefs that you put out into society? This is the perfect storm in terms of scientific knowledge or its lack, and understanding the arguments on all the different ways that particular recommendations translate. But this isn't a new thing. This has always been the case, that science is political. This is a picture of protesters during the Scopes trial, right? Something that maybe doesn't impact us on a day-to-day basis, but in terms of fundamental questions about the universe and evolution. It's interesting in modern controversies, oftentimes people who are creationists will argue, teach the controversy. I think that would be the most wonderful thing in the world, is to understand the process and the controversy, not teach people that evolution is true, but understanding why when you look at different arguments, parts are there or not. And yet most of us didn't probably get the detailed arguments back and forth in school. And definitely, this has gone back as far as science has existed. This is a picture of Galileo, who is considered one of course, the main developers of science. And remember that he was sent to prison for advocating the idea that the Earth was not the center of the universe, supporting ideas that were originally created by Copernicus, but then he showed evidence for through the invention of the telescope. So these ideas, these controversies have always been with us. And they're not just about esoteric issues, like the universe and evolution. They impact us on a day-to-day basis, and they definitely play into our roles as doctors. The role of cigarettes in causing cancer was something that was fought out scientifically and in the press for decades before it became the sort of standard consensus, and that smoking has started to disappear, at least here in California for the most part. on a large-scale basis. I am old enough to remember those, quote, smoking and no smoking sections where a magical invisible line supposedly separated you from the giant blue cloud of smoke that was out there, and that it was not uncommon at all to see, even in prominent news articles, that the science about smoke, even as a direct smoker, and cancer was quote not settled, and that some people claimed that it still had health benefits and could get plenty of doctors to show up on TV or other interviews or write articles to say that that was the case. But there's a lot of baloney out there, and a lot of it can look good. I don't have the sound for this, but I'm just going to show a little video on here that about something that's been out on the internet in this terms. Right. So thank you to McGill University for producing that. As you can tell, that was a fake video of a video about fake information. But you will see this sort of thing a lot in terms of things that look scientific but clearly aren't. But oftentimes, I love the fact that they have the part about the blue liquid in there. For some reason, every picture, if you Google, of a scientist has a person, usually a white male, staring longingly into a test tube filled with a blue liquid. And this is used to support the various conspiracy or other generally baloney information that is out there. But despite all the nonsense that swirls around, of course, we're aware that in the real world, science has done amazing things. I threw up some pictures of some ones here, Watson and Crick. Does anyone recognize the person as a medical providers below Watson and Crick there down here? That's Alexander Fleming, the person who produced penicillin. This is Marie Curie, who was not only the first woman to win the Nobel Prize, but the first person, period, to win two of them. This is Johannes Salk, who created the Salk polio vaccine. The books Principia, Newton's really revolution on everything when you think about it. The book from Darwin's The Origin of the Species. Everybody knows Einstein. He finally developed a theory about space. It was about time too. Sorry, bad science joke. And then, down here, the landing on the moon was really a product of science, not so much a scientific endeavor, but an aspect of engineering. And I'm going to talk as we go along as one of the learning objectives, if you actually saw this ahead of time, to understand the difference between science and engineering. But all this stuff, we know it's important, which is why we teach it in school, right? Why these young ladies are looking, admiringly at this young man, as I thought somehow people would do if I became a scientist early on. That we think, hey, we'll offer a lot of science courses in school. But when you get into the science and you learn it later and you learn what science really is, you'll discover that a lot of what you were taught in school isn't really science. This is one of those callback things here, but you say, well, I took a whole lot of science, not just kindergarten looking through a microscope, for goodness sakes. How many people took physics? Or physical chemistry, or organic chemistry, or biology, or biochemistry, or anatomy, or geology, or microbiology, or pharmacology, physiology, pathology, computer science, and psychology, right? Now, this is a mental health lecture. I have the Krebs cycle up here. It occurs to me how many times in my life I have memorized the Krebs cycle in basic biology, in AP biology, in college biology, in biochemistry, in my PhD biochemistry class, and in med school, and I still couldn't reproduce this thing to save my life. So a lot of what sorry, was someone speaking up? All right, won't worry about that too much then. But a lot of you took these courses and you think, oh, well, I learned science. But for the most part, you didn't learn science. You learned a lot of scientific facts. You learned, again, how to reproduce the Krebs cycle, or back here, the hierarchies of need, or the structure of DNA. But learning facts is not really learning science. It's learning stuff that was produced by science. But as the quote here implies, science is built of facts the way a house is built of bricks. But an accumulation of facts is no more science than a pile of bricks is a house. So again, what we learn in school is really things that we're taught by virtue of authority. We're taught in a lot of ways this is the case, but why do you believe that that's the case? And in some cases, we do get more into the weeds. And so how many of you took an actual lab in school that took physics lab or chemistry lab or anatomy lab? Like here, how many of you dissected a fetal pig when you were in high school, or cat or mouse or whatever it was? And why do we do that instead of, hey, we can draw pictures in the book? We do that because a really important part of science is reproduction, is being able to show people that it really does happen in real life, and that this happens over and over again, and that the heart in the pig or the cat or wherever is the same way that it actually is in the textbook, and this isn't made up. Because we got that wrong for thousands of years. Galen was considered so correct on a topic that even though people, could look at a cadaver and say where certain things were, because it was in the textbook that had been written by Galen, no one challenged this despite the evidence of their eyes in front of them. But we may reproduce some of these. This is the milk and oil drop experiment, if anyone did that in a physics lab. So you may think, well, no, I really did this. If you worked in a biology lab, you may know what this motion is, pipetting, right? Get pipetter's thumb after enough of this. So you may think, oh, well, no, I took lab. I understand science. But that's not really the essence of science either. That is scientific technique. And technique, again, just like facts, are critical to science. If you can't do stuff the right way, or if you don't know the basis of the facts, you can't do science. But that is not the essence of science. Okay. But now, how many of you learned about Ibn al-Haytham or Francis Bacon's conceptualization of the scientific method? How many of you learned the difference between inductive versus deductive reasoning, or what eliminative induction is? What's the difference between a fact and the truth? What's the difference between a hypothesis, a theory, and a law? The difference between science and engineering? How many of you learned Newton's reasoning and philosophy? Or, as I'll put at the end, Carl Sagan's rules for baloney detection? If you did this, you got a lot closer. because in the end, science is philosophy. Science is an idea about how we advance concepts of truth. It is a tool for developing facts, and it involves these various philosophical ideas. Now, in terms of the method and the philosophy, as has been pointed out, there is no one scientific method, and therefore you're not going to learn entirely to be a scientist from this lecture or even from reading those books. But this comes a lot closer to really understanding what science is not learning the piles of scientific facts, not learning how to use a pipetteman or to do an oil drop experiment, but learning the thought concepts of the philosophy of science. And that is what's really useful in all of this. So finally, maybe how many of you asked a question that you did not know the answer to when looking at science? You set up an experiment to answer that question, asked a lot of people to point out everything that was wrong in the way that you were going to set up this experiment, revised the experiment based on that feedback, performed the experiment, repeated the experiment to see if it was just a fluke that the first time you did it, but you did it over and over again until you show that it was consistently right. Settled your own bet with yourself about what you said you didn't know, and were open to the idea of that whichever way the experiment went, you would alter your beliefs on that. And then whatever you came to in terms of conclusions, tried to think about all the ways that you still could be wrong. And then when you think you figured out all the ways that you could be wrong, you throw it out to the wolves, to lots and lots of people who could thought you could be wrong. By the way, one of the big differences between presenting in front of a medical audience and a PhD audience, I remember I think I came across as probably pretty hostile when I first showed up at Naval Medical Center in residency, because in PhD programs, grand rounds is a long exercise in attacking the speaker. But then based on those attacks, we should revise our conclusions, admit your errors, and then start the whole process over again. If you've done that, congratulations, you are a scientist. Or a researcher, because scientists got obnoxious about other people stealing their terms for things like Scientology and changed our title. But that's really the only way to learn this in detail. But we're going to try some crib sheets. We're going to talk about the philosophy of it, because really, who has time to do all these steps every time you have a question? You can't. Even Carl Sagan, Isaac Newton, anyone had to rely on each other to do this. That we cannot say that every time we come up with a question, does this new vaccine work? Is global warming true? That we can go and do the experiments ourselves. I'm not going to take 10 years to learn the techniques of what goes into the science of global warming. But if you understand the concepts behind it, you're still able to read the literature and really sort out what is being spun and what is the scientific consensus. We can rely on each other. Whereas Newton himself said, perhaps the greatest scientist of all time, if I have seen farther than others, it is by standing on the shoulders of giants. That we have to learn to be able to understand appeal to authority, even in science. Even though challenging authority is one of the fundamental concepts of science, that we still have to be able to understand when authorities can be trusted, what facts that we can start off with. But we do have to understand the first concept, which is that there are no truths in science. There are only facts. And that may sound strange based on common English. It's like, well, what is the difference? Isn't a fact what is true? Not exactly. Because this gets into the concept of axiomatic things that basically could not be untrue in any universe. The way that in a planar world that all angles of a triangle equal 180 degrees. There is no universe, there is no way that cannot be true. This is an absolute truth. It is axiomatic. It is depended on to the point that we cannot challenge it. Whereas when we talk about truth in science, what we're talking about is the current when we talk about facts in science, we're talking about the currently agreed upon concept of what is true. But one essential aspect to science is that all facts, if they're scientific facts, must be falsifiable. There must be a way to say, well, we believe this, but it's only considered a fact if there were some challenge to it, that if this turned out to be the case, that we would no longer believe that. An axiom will never be open for debate. All facts in a scientific sense are open for debate. And to be able to do this, we first depend on the concept of natural philosophy and the objective observer. This is the grainy picture of Bigfoot, which of course most of us don't think is a scientific fact, despite the fact that you're looking at a, quote, photograph of it right there. But before we figured out a lot of the concepts of science, the natural philosophers, the precursor to what are today called scientists, in fact, probably Newton and Copernicus and many others would have called themselves natural philosophers. We're dependent on this much earlier idea that goes back at least to Aristotle and probably lots of other cultures as well. That didn't get popularized as much because they didn't carry on in the Western canon by virtue of being invented by white males. But it was probably an idea that's been around a lot longer, that to be able to have any sort of argument about things, that you have to agree first of all on what we can actually observe and what we can observe in the physical world and who is a reliable reporter of this. If somebody has a motivation to fudge a photograph, if somebody has schizophrenia and is reporting that they have seen this in front of them, why we cannot consider them reliable reporters. And that we first do depend on saying that we have to trust each other, that in this world of science that no one person is considered infallible, but that if you've gone through a certain process, that we gather certain letters behind our name, we will trust you at least to report on what you observed with your own eyes, ears, and instruments. If you don't believe that, it's hard to have any other sort of basic debate. If you believe that the CDC is overtly just making up numbers about coronavirus, you can get into how they got to those numbers. But if you believe that whoever's communicated them is just picking these out of a hat, you can really never have any future discussion about any other scientific aspects, because you have to agree on what your observable aspects are and believe the concept of a reliable reporter. That if enough people, who generally seem to be people who are credible, have said something, that we'll believe that that actually has been observed, but that we're never going to trust one person, and that anything that seems exceedingly out of the ordinary will require more observations. Some of these things have been missed, that people didn't believe that meteors hit the Earth because it was only some farmer out in a field somewhere who reported this, until this started showing up hundreds and hundreds of times. But something that seemed more likely, I think I saw lightning go to the left versus the right, more willing to accept one or two observers on. But it requires observation, as it requires it to be in the natural world. That science cannot comment on things that are considered supernatural. Now, if something happened, though, no matter how unusual it would be, if God physically showed up tomorrow and told us, yes, I created the universe and you're wrong about Heisenberg's uncertainty principle, then there's still a physical, observable God in front of us, or a ghost, or anything else that could be considered supernatural would no longer be supernatural, it would be observable. But in terms of things that can't be observed, science cannot comment on that. We must start from the basis of natural philosophy and observable. And this requires consistency, what we call reliability, which is why, as psychiatrists, we have the DSM. Because this ended up being a reason that our particular field was a big mess to begin with, is that we were reporting on treatments for schizophrenia, but what one person described as schizophrenia and what another person described as schizophrenia were entirely different things. So it wasn't surprising when one doctor said, well, my new method of psychoanalysis cures schizophrenia, and another doctor would say, that's nonsense. I've tried this thousands of times. It does not seem to work. Well, that's because our definitions aren't agreed on. So one of the fundamental things is we first have to agree how to be reliable, how to measure things in consistent ways. If we say the length is 5, the other person says the length of 6, we have to say 6 whats. And this is why in psychiatry we've come up with very specific definitions of things, that we have to agree what something is in a particular way. Even if you think this is very dry and really doesn't describe it, it first has to be reliable for us to be able to have any other further definition of what a doctor in Peoria thinks is schizophrenia has to agree what a doctor in Timbuktu agrees is schizophrenia, and therefore we have to have rigid definitions, rigid units of measurements. But natural philosophy, the idea that you needed to measure things and you needed to rely on the physical world, is an idea that has been around, again, at least since Aristotle, so several hundred years BC. But if you look at, we think of science as changing the world, and we look at basically all measures of things that we think of being the product of science. The improvements in life expectancy through medicine, gross national product and our ability to produce things, people not living in extreme poverty, the amount of energy that a society uses. Though it's not a positive aspect of science, but war-making capacity, how destructive can we be, and societal progress in terms of things like living in democracy. If you look at these graphs, you'll notice that everywhere from 1000 BC to up about, somewhere between about 1600 and maybe about 1800, these graphs are sloping up very, very slowly. And this uptick did not occur with natural philosophy. If you look, the scientific revolution on here occurs about the 1700s, which is where we start to see this upward curve. And we'll talk about why there was this gap before you see the sudden upshoot a little later. But natural philosophy did not change things in a tremendous way. Science did. So what was difference between natural philosophy and science? Well, a lot of it comes down to the difference between deductive and inductive reasoning, and accepting the idea of inductive reasoning. So deductive reasoning was what Aristotle and Plato and St. Augustine would have considered the ideal form of reasoning. It is reasoning that is absolute, that starts with axiomatic truths and builds on them in ways that if you put them together, there is basically no way to be wrong. And the ultimate example of this is geometry. If you've done geometry proofs in school, you have done deductive reasoning. You've started with, okay, if we know as an certain things that a number is always equal to itself, some very basic axiomatic truths, you can actually figure out a lot about the universe. But there are limits to this. And this is why Aristotle, despite the fact that he was a brilliant man, got stuck with the idea that eels don't reproduce, because he started with axiomatic truths and reasoned forward to the way the world must be. Probably his most famous error was the fact that he started with the idea that men are superior to women, and therefore men have more teeth, without actually ever counting the teeth. But I like this example because it's a little less political. But he was sure that eels don't reproduce because they had dissected eels and there were no gonads. And he started with the fact that all creatures that reproduce have gonads. Eels don't have gonads, therefore eels don't reproduce. If all those things are true, that would be absolutely correct. And it, by the way, did take until about the last 10 years until we actually figured out where and how eels reproduce, because they do it at great depths and generate their reproductive organs later. But these put us down a dead end because we put us in places where we're like, this must be true. And in science, nothing must be true. We have to always challenge ourselves. But we use what it was generally considered a more flawed form of reasoning, of inductive reasoning, which is basically allowing our experiences to shape the way that we think. And generally, the person who is thought to be the first person to really put this into effect, to say that in a systematic way, we're going to at each point challenge our belief by particular experimentation and measurement, was I'm never quite sure how to pronounce his name, but Ibn AL-HAYTHAM, I believe it is. And he's considered by a lot of standards the world's first scientist. And he started with pointing out that you could not depend on appeal to authority. You could not believe that anything was absolutely true. The duty of the man who investigates the writing of scientists, if learning is the truth of his goal, is to make himself the enemy of all that he reads, to attack it from every side. He should also suspect himself as he performs his critical examinations of it, so that he may avoid failing in either his prejudices or his leniency. So again, I talked about that earlier in terms of, have you done this as a scientist? Have you challenged everything that you believe, or as you go into it, started to really sort of attack all ideas from all sides? He started with that concept, but also he really altered his beliefs by experimentation, but in a systematic way. And that was, a lot of other people had looked at one thing at a time, and said, oh, well, this shows this. But what this scientist did, this first scientist, was really take a systematic approach where he took things step by step, and with each experiment he would alter his beliefs and then create a new experiment to test the next one in a row. And he worked in terms of optics. So I mentioned that light ended up being the light of science in a lot of ways, that he was the first person to really figure out the concept of a camera lucida, why images invert, to get the idea that light travels in a straight line, and that this is how it impacts our eyes, to understand physiology as well. So came up with some tremendous advances. And if you look at his lifespan, between 965 and 1040, so quite a long time ago, was really creating some amazing steps forward. Unfortunately, if we go back to this graph here, you'll notice that the scientific revolution, he said, started here, and hey, he was back here. Science was invented a lot earlier. Well, unfortunately, he was kind of like the way Vikings, or maybe ancient Africans or Polynesians, whoever we believe hit America first, were compared to Columbus. It doesn't matter if you were first, if other people weren't able to pick up on your ideas, if it did not spread, that sort of thing. So unfortunately, for a long time, his ideas never spread to the West, even though the idea of inductive reasoning was out there, but it was considered inferior. And inductive reasoning reverses the if-then statement. In deductive reasoning, we say, we start with the truth and we say, if this is true, then this other thing must also be true. Where in inductive reasoning, we reverse that and go, okay, this is how I think it works. But if that's the case, there's a result, and I'm only going to believe my original postulate if, in fact, the final result turns out to be correct. Otherwise, I'm going to throw this apart, and creates a structure of how you think about, like, okay, this is how I'm going to think the universe works in general as a great concept, and that's a theory. A theory is the concept of how an entire structure works. Something that happens so often that it turns out to be axiomatic is a law. So these are different from individual tested hypotheses, individual tested truths. When AL-HAYTHAM was testing things, he wasn't looking at just one question. He was looking at, this is how light works, a whole theory of light, a concept of light that was tested through individual experimentation. And he found certain laws, certain rules, that light always seemed to travel in a straight line. And based on that, was able to create a system of understanding the larger universe, but only in that one niche, and unfortunately it didn't spread very far beyond the Middle Eastern world at that time. This requires hypothesis testing, and it is fundamentally flawed from a philosophical perspective, because you can never be 100% sure that any of your truths are going to be there forever. But it is much more useful on a day-to-day basis in terms of being able to alter the universe. Quote by a famous psychologist, William James, things are true to the extent that they are useful. I don't know if that is true from an absolute philosophical point of view, but from the point of view of science, a lot of the success of science, the reason it became so successful as a philosophical school, is actually sort of circular, is that science says that things that work, we're going to view them as true, and science itself worked. It allowed us to produce these amazing things. So again, just want to look at these broader concepts again, though. So a law is something that is as close as we get to an axiomatic truth in science. That an observation that is made so often that it is presumed to be a universal truth. For example, that Newton observed that every time there was an action, there was an equal and opposite reaction. That is one of Newton's laws of motion. It's something that all of his other ideas depend on. And again, it has been true so many times that it seems to be unchallengeable. A theory. Now, based on these laws, he took a larger concept of how the universe worked, and his theory of gravity explains the universe via the idea that forces can act at a distance. And this contrasts to Einstein's theory of relativity and the idea that the concept of how the universe worked is explained by the curvature of space. And by the way, the current theory of everything, of how everything works, is basically divided up into two camps, what's called the standard model, which explains things on everything from quantum level up to everyday things, but cannot explain gravity and larger space, which is still explained by the theory of general relativity, these larger concepts of how the universe works. But we haven't merged these concepts into a universal theory of everything yet. And that sometimes gets confused with a hypothesis. A hypothesis is a proposition that will be tested. And sometimes people will say, well, it's just a theory. Well, everything in science is a theory or a hypothesis or being tested. So if someone says, well, the evolution is just a theory, point out that gravity is also a theory. It's a concept of how the universe works, but it's one that has really seemed to work and be useful on a larger level. Note that science itself is a theory. It's a concept of how the universe works, that again, that inductive reasoning and that particular methodologies can actually teach us things about fundamental underlying structure of the universe. You could go back to Plato's cave and argue that, our observations could all be wrong. All of this we could all be living in a hologram or the Matrix or whatever. But the theory, that physical observation, that rules of logic, that experimentation actually says something true is a theory. It's a way of understanding the universe. So even if that theory says something about God playing dice with the universe in terms of quantum mechanics, that it still implies that there are rules, even if those rules involve a certain degree of randomness. Now, I want to get forward into how this came to the West and how this started to change the world, which comes to the science of Bacon. Not this Bacon, but these Bacons. And this gets confusing sometimes because there's both Roger Bacon and there's Francis Bacon. So Roger Bacon was known of by Francis Bacon. Maybe he looked up the fact, hey, we have a similar name. I wonder what he did. Roger Bacon was one of the first people to actually translate the ideas of AL-HAYTHAM, the scientific method, into Latin, the language which was generally used in academics throughout the West, and therefore allowed it to be accessible to a large portion of the Western world at that time. But Francis Bacon was the person who wrote these down in terms of rules and what he first called the scientific method, and maybe what you learned then at school in scientific method. And a lot of people will say, if you Google who invented the scientific method, the answer you will often get is Francis Bacon. But this is what he originally wrote down in Bacon's Novum Organum. Three things there were three steps to doing scientific discovery, which is that first we gather and describe facts, that we classify those facts into three categories: the presence of the characteristics under investigations, the absence of the characteristics, or the presence in varying degrees, and that we reject whatever applies in light of these tables not to be connected with a phenomenon. What? That doesn't sound like the scientific method I learned in school, right? Well, give them some slack. It was the 17th century, and even into the 18th century. I'm not going to go over Newton's principles of scientific philosophy, because also they're pretty dense, and most of it it was synthesized in these general concepts that science is about what we don't know. If you go into it presuming that you know the answer, it's not science. It's about discovery, and what developed into the modern scientific method, which isn't really as simple as this, but this is what is generally taught in terms of first you ask a question, then you do background research, gather those facts. All those scientific courses that you took were not wasted. If you want to be a scientist, you still need all those facts and do the background research. You construct a hypothesis, test with an experiment. The idea has to come before the experiment. If you're backwards reasoning, you're much more likely to make an error. You determine if it's working, and this is the key part, is that you must be willing to believe your answers. There's no much how much you loved your idea or your theory, is that any beautiful theory, any beautiful hypothesis can still be slain by an ugly fact, by an observation. You draw conclusions, come up with other ways to challenge those communications, and then finally, only after all these steps are done, do you communicate the results, and the cycle starts all over again. That may be an idea that was familiar to a lot of people from school. But again, a lot of us never really do that. At least I didn't until I became a graduate student. We end up gathering the facts. You are here, do the background research. And again, those are really, really important. And you're at the bottom step as well. You're ending up communicating those results. So we skip all the scientific methodology in the middle, but on a day-to-day basis, we use the scientific facts to our advantage. And this is engineering, and may have actually been a more important development even than science. You couldn't have done engineering without science. It's not modern engineering because you required a lot more of these findings. But basically, once you know some fundamentals of the universe, once you figure out concepts of electromagnetism, the transistor can be invented, but then someone has to actually put all those transistors together to actually create a computer. And this is where this lag comes in between the scientific revolution and the industrial revolution, is that engineering is what really, the translation of science is knowing those facts, is what practically changes the world. From a scientific point of view, you may be able to do some esoteric fun things, but from an engineering point of view is where things really become solid and stay there. And we as physicians, psychologists, nurses are biological scientific engineers. We are taking those facts that most of us have not spent a ton of time in a lab actually working out and arguing about, but we learned, anatomy works this way, this drug this way, and we put it to practical application, which is actually an even more powerful way to change the world on a day-to-day basis. So this is why we are able to get away without teaching real science in school, even in medical school, even in nursing school, but because we can do engineering based on those facts. That's why I went back to medical school after being a graduate student, is that I was sick of being poor and not being able to do anything with this. Figuring out, spending 5 years figuring out one tiny little fact and not being able to apply that to the real world. And also it just doesn't pay well, as this gentleman saying that he will do Higgs boson particle explanations for food will demonstrate. But don't be too proud of yourself. There's lots of other things that translate to society. The scientist may be able to do the cool tricks. The engineer may create something that's much more stable, but then business translates into something you actually want to use. Beer in the cup, liberal arts may still be left out in the cold to some extent, waiting for their tips at Starbucks. And now I want to make us talk about the fact that most of the people here are working, of course, in a biological science, and specifically in mental health science, which is often where we just say, well, it's not scientific. We can ignore all this. This is a different process, but I'm still useful to my patients and to my clients, to which, of course, the biological scientist is just aghast and will point out that the principles and concepts in biology are the same as in physics or in chemistry. We're doing the same things. Sometimes I'll point out that psychiatry is actually probably the most scientific of all the medical specialties. And that's because science isn't about what you know, not having an accumulation of facts. Surgeons might be the best engineers, but science is about what you don't know and having to critically think things through to figure them out. The problem with biology is its level of complexity, and how complexity ends up playing into why theories and concepts that can explain the whole thing are so much more difficult in biology in particular, in mental health issues. So in physics, there are things that are immensely complicated. That the Milky Way galaxy has 100 billion stars in it, which nevertheless physics is able to perfectly describe the way that the galaxies orbit each other in different stars, with some exceptions about dark matter now, et cetera, et cetera. But there are as many neurons in your brain as there are stars in the Milky Way galaxy. And then when you look at something like synapses, there are orders of magnitude differences in terms of the number of. There are 200 trillion synapses in the human brain. That is basically the most complicated single object we know of in the universe. So being able to predict something that, at a biological level is incredibly complicated, especially when we realize that you can never know all the basic facts at an absolute level. And again, we think about this in terms of physics and the Heisenberg uncertainty principle. That's what this equation is, or at least I think it is. I'm not really sure it's the uncertainty principle, but you get my drift there. That on a molecular level, when we're talking at the brain, we're never going to know exactly where every atom or electron is in space. So there's going to be some error at this small level. And unfortunately, the other piece that ties into this is chaos theory, is that a lot of physics, the way it was worked out, was linear equations, right? Things that follow a predictable pattern in math. But a lot of systems are non-linear. The weather is a non-linear system, which is why it is almost physically impossible, no matter how good that we get, to ever say that we will ever be able to predict the weather beyond about 14 days. You might be able to predict the climate, that's a separate issue, but to actually be able to tell you it's going to rain on a Tuesday 2 days from now is almost impossible, because the math becomes essentially infinitely complex, and tiny effects, the butterfly effect, right? No matter how much you measured in terms of what you think the weather's going to be next week, that one flapping butterfly that gave you different information comes up with a dramatically different result. The butterfly flapping in China alters the rain in America, or maybe a virus that started in China altered the course of civilization here. Complex relationships, human interactions, neuroscience is incredibly complex. Thus, it is actually, when people say, if we could put a man on the moon, we could do this, right? I don't know what people said, by the way, before we put people on the moon. What did they say? If we can do blank, we can do blank. But if we could, putting somebody on the moon is actually a much easier task than figuring out whether another human being is going to commit suicide. It is very complicated, but it's still the same principles of how we get there still apply, the same thought message. So what does any of this have to do with COVID, vaccines, masks, et cetera, believing this new science that's coming out, being able to read this, being able to translate this to our patients in terms of what we tell them that is actually true? And as I said, you may have learned the basics of the scientific method, but really it comes down to being able to think in a systematic way, to coming up with what Carl Sagan called the rules for baloney detection. And following these things to read through newspaper headlines, to read through journal articles, to read through what a presenter at Grand Rounds says, and be able to challenge those ideas. So, and it starts, as I talked about, in terms of natural observation. We must agree on what the facts are. There must be independent observation of it. And that we must encourage debate, that we can't just say that anything is a settled truth, that all things must be up for challenge, and we must look at them from as many points of view. Arguments from authority carry little weight. Authorities have made mistakes in the past, so even though Galen was right about a lot of things in medicine, we can't simply say, well, Galen said it. And we also, similarly today, can't say that, well, Fauci said it, or Trump said it, or whoever it is you believe. We can't rely on that person. There are variations of that, and the reasons why something that has worked in the past may be more reliable now. A person who was correct in the past may be more likely to be reliable now. But if you actually understand the weeds of it, that just because an authority said it should never stand up. There should always be multiple ideas. Spin more than one hypothesis. If there's something to be explained, think of all the different ways in which it could be explained. Then think of tests in which you might systematically disprove each of the alternatives. That which survives, the hypothesis that resists disproof in this Darwinian selection among multiple working hypotheses, has a much better chance of being correct. We look at things at multiple perspectives. Try not to get overly attached to a hypothesis. This is very hard. We all love our own ideas. We all live in bubbles now where we reinforce our own ideas. But if you're going to think as a scientist, you really have to accept the idea that you could be wrong and be willing to reject your entire life's work and its system because something new came along. We must do it systematically, try to quantify things. Again, try to use things in a measurable and consistent and reliable way. Even in mental health, we have psychometrics where we say, well, when we say somebody is experiencing something, how are we quantifying that? How are we saying that this is the same way? If there's a chain of argument, every chain must work, including the premise. So if one thing is wrong in there, the whole thing falls apart. Again, EELS do really reproduce, despite the fact that, the idea that something without gonads cannot reproduce. What was missing in there, what was an error is, well, because something doesn't have a gonad when you dissected it, means it never can. That one piece in there, the whole Aristotelian idea that eels don't reproduce, fell apart. Occam's razor, a lot of people have heard of this, and you hear this all the time in terms of rules that when faced with two ideas, that the simpler one is more likely to be true. Not always, but more likely. And always, always, always ask if the hypothesis can be falsified. If you're not willing to accept that you could be wrong and say, if this is true, I will change my mind, you are not being a scientist. You are working in axiomatic aspects, in ideas of faith. And I'm not trying to challenge your faith in that regard. Faith is a beautiful thing, but it's not science. And you must be willing to accept that you're wrong. Now, if you go through Carl Sagan's, again, The Demon-Haunted World, a beautiful book. Man, that man could write. Has a great step-by-step things on a number of logical fallacies, ad hominem, argument from authority, argument from adverse consequences, appeal to ignorance, special pleading, begging the question, observational selection, statistics of small numbers, misunderstanding the nature of statistics. This is why, hopefully, as part of those tools that we all took, we took statistics in addition to science labs, inconsistency, non sequitur, post hoc, ego, propter hoc, meaningless questions, excluded middle, false dichotomy, short-term versus long-term, lots of things that I don't have time to read the whole slide on. Excuse me one second. Excuse me. All right. Going on, slippery slope, confusion of correlation and causation. You hear this a lot in terms of challenges. Straw man arguments, suppressive evidence, weasel words, a lot of things that are worth looking into. As I said, there is no way to be a scientist based on the simple method, on a few sentences in philosophy. A lot of this is learned over time. But a lot of the intellectual arguments have been sorted out. And you can read them in textbooks, and you can use these thought tools. The same way we teach cognitive behavioral therapy to manage our emotions, we teach science as a way of understanding truth, of understanding arguments, of breaking them down. This is my shortened version of it. Dr. Captain Doctor's shortened version for medical providers is that with any of topic that you're coming into, whether vaccines work, whether masks work, whether a new drug that's been introduced to market is useful, whether we should use medications in children, any of these things, you have to go in with an open mind. We're all going to have biases, and there also doesn't mean that we should just toss out everything we've learned before, but you have to go in with an open mind, but not so open that your brain falls out. Try to be aware of your own biases in there. We will always fail at this. We're always going to be prejudiced towards our own ideas, but to the extent that we can detect them, we should. Don't pay attention to one finding, one new paper that comes out in the new exciting hot thing in the news, unless you really understand the rest of the field. That one new paper, one new finding, one new headline might change everything, but it doesn't mean that it did. You have to understand the context in which all of this exists. Always ask compared to what, when something comes out. And the way, by the way, to get to a lot of this, when a new statistic comes out that, oh my God, 5% of the population is dying from this, what's that mean compared to natural deaths that occur. What does this new article mean compared to how many are there out there? A very useful tool in all this is looking at the larger literature. And two great ways to do that, if you learn nothing else from this lecture, I would say anytime you see new information, go to one of two places. Go to PubMed, if we're talking medically, by the way, PubMed or Google Scholar, because almost all reliable scientific arguments will end up for biology in those two places. And you see there's new things that can come out. You Google your topic, but add that word scholar first, scholar.google.com, and you will avoid the Scientology nonsense and come up with all the actual scientific papers, of which there may be some very legitimate disagreement. But when someone says the scientists on my side, if you'll do a Google Scholar search and you see that there are 5,000 articles that support that vaccines do work and 3 that support that it doesn't, you may understand that, okay, maybe that one that was in the news was a biased representation, or the one that the drug rep just gave you, right? Because he or she wants to sell their product. In doing this, understand Cochrane criteria. That's a whole separate lecture I don't have time to do, but in terms of weighing the level of different papers and why a review article that's done by Cochrane criteria, looking at meta-analysis, is really the gold standard of how you add up thousands of contradictory pieces of information. But again, going back to going into an open mind, make a bet with yourself. When you go into this, say, okay, there is this new thing that's happening. I think it might work. I think it doesn't work. I believe this. And this is how I'm going to settle it. I'm going to actually, say, measure this in my own clinic. I'm going to not just go off my base assumptions, but I'm going to make a bet with myself in terms of believing the experimental results and looking at that. And that bet might be in terms of the number of papers that are out there. It might be in terms of adding up all the data. It doesn't have to be a traditional experiment, but it's still being open to inductive reasoning. The idea that our new findings will change your beliefs about things. So this is now the time where we start to put this to work, and hopefully people will come back online and we'll talk about how these methods apply to particular things that have come up. So can someone chime in to let me know that, hey, you can actually still hear me? I haven't been just talking to my computer screen for an hour and 12 minutes, and that you're going to participate.
You are alive, and I hear you.
Excellent. Okay. So problem 1, ripped from the headlines, right? Something we see in everyday life. You walk into a perfectly nice restaurant. However, you immediately spot a sign that said, "This facility contains chemicals known to the state of California to cause cancer." Your friend urges you to leave immediately. There's a scientific statement there that there are materials here that are known to cause cancer. What do you need to consider before surrendering your meal? What are the sort of scientific ways that we look at that are connected? Anyone want to chime in? Deafening silence. Okay. Well,
I would say what things exactly here?
Right. So what specifically? How am I going to be in contact with them in that regard?
Right.
But let's say, okay, it's at a gas station, and we know that gasoline is one of those things that can cause cancer. Does that mean it's going to cause cancer in you? How was that established? A lot of these things were done by, say, the Ames test. So, yeah, they cause cancer cells to reproduce in a particular way, but you're probably not drinking the gasoline. You're probably not bathing your cells in the gasoline, maybe exposing yourself to some fumes, but also there's going to be a relative risk in everything in life, right? So just because something happens on some scale, that has happened somewhere in some way, does not mean it will happen to you. Again, if we look back at that sort of faked video, or we talk, a lot of times you'll see these things about, this has this effect on DNA and therefore it's doing this. Well, yeah, it had the effect on DNA in a test tube, or something killed cancer cells. Does that mean it's a cure for cancer? No, that scale and context and your exposure all matter in these regards. So something as a broad scientific, that it occurred somewhere, that's reliable. I'm sure that these chemicals that are in a store or a restaurant did cause cancer cells to divide some way, but that doesn't necessarily mean it applies to your specific situation. You have to understand the context. So, problem one. All right, another ripped from the headlines thing that's September 14th. Newspapers reported that on September 14th, 4 scientists uploaded a document entitled Unusual Features of the SARS-CoV-2 Genome Suggesting Sophisticated Laboratory Modification Rather Than Natural Evolution and Delineation of its Probable Synthetic Root to Zendo.org, which is an open access repository for scientific papers. A lot of scientific information in here, and claimed, therefore, that there is now evidence that COVID-19 has features indicating it was in fact manufactured as a bioweapon. Based on this, should we go to war with China? Or what could be wrong with this argument?
I mean, if it's an open access repository. Yeah. Anybody can upload it because they have access to the website.
Exactly. So even though this was a repository of scientific information, and that's a wonderful thing because peer review is a painful and slow process, that this made headlines because it was on a scientific website, but it turned out the people who uploaded it were really political hacks. They weren't really scientists at all, and they weren't analyzing new data. They were basically going off interpreting other papers that had similarly been posted and just coming up with a new interpretation that really had no logic to it at all. But starting with that reliable reporter concept is, where did this information come from? Just because it has scientific words behind it or it appears in a place that maybe scientific things go doesn't mean that it comes from a reliable reporter. Know your sources. All right, study number 3, or problem number 3. Real one. I tried to be balanced a little bit in terms of attacking liberals versus conservatives and their beliefs. So this is something that made national news recently. A study recently came out from the Proceedings of the National Academies of Science. Big, important journal, not like this data repository. We're pointing out that African-American babies are half as likely to die when they are assigned a physician who is African-American as when they are assigned a physician who is white. Now, based on that, an African-American patient of yours asks if she should immediately, therefore, leave her OBGYN, a white physician, and seek out an African-American doctor. Will this improve her outcomes? And again, I'm not dismissing the reality of racial disparities in all this. But what was wrong with the science here?
What's the process of assignment, and is there some bias introduced there?
Exactly. So to begin with, this is a classic example of correlation and causation, by the way, is the short answer, but that was in fact also a flaw in it. Even if it had been done correctly, there was the correlation and causation thing, but this was pointed out later that the assigned physician, basically the person listed as the doctor of record on there, was not actually necessarily even the doctor taking care of the patient. So how could that happen? There's also a plausibility issue in terms of, obviously there have been generations and generations and generations of bias, and statistically African-American children have been at higher likelihood of infant mortality than whites, and the idea that you could reverse all of that by just assigning a different physician. So in terms of plausibility, there were some issues. But the big one is correlation. And it turns out the easiest explanation for why this might be the case is, unfortunately, via bias in medicine, is that a lot of intensivists, if you look at, we're doing a better job of getting African Americans into medicine in general, but still not a good enough job by any means. But if we look at the sort of high-paying jobs, there's still a lot more bias in that. Intensivists are much more likely to be white than they are to be African American. So who takes care of the sickest patients, the ones who are most likely to die? People who are white. So, again, there is a correlation versus causation issue in this study. It's interesting in terms of this, by the way, in terms of reliable reporter. You really have to know the details of this a little bit. The National Academy of Sciences is a collection of very, very prestigious scientists. They publish their own journal, and it's generally considered an incredibly high impact and difficult journal to be in, with one exception. If you are a member of the National Academy, you're allowed to publish one paper a year in that journal, which is not peer-reviewed. So a lot of the challenges for things that normally would have occurred to this paper did not, because the person putting it forward was a member of the National Academy, someone who was considered very reliable, and an example of where appeal to authority also ended up causing us a lot of problems. Problem 4. Something else that we did a lot, at least when I was at Navy. You have paid to go to a psychopharmacology seminar in which the speaker notes that among antidepressants, there are essentially 3 known mechanisms: increasing dopamine, serotonin, and norepinephrine. He points out that by mixing 2 different antidepressants, it is possible to get all 3 mechanisms at once, and that this will now give us the best possible antidepressant in existence. Should this be your first-line treatment? What is wrong with that argument?
It's an untested hypothesis.
Yeah, it's deductive, right? It includes that if all these things were true to begin with, yes, that would lead to be the case. It's a good way to generate a hypothesis. But the idea that based on mechanisms that we're going to be able to necessarily absolutely produce the same sort of consistently reliable results in biology than say that they do in physics is simply not the case. There are lots of things that have seemed like they should work, haven't. And even in terms of what we think of the mechanisms of drugs have turned out to be wrong. I mean, gabapentin, right? It's named that way because we thought it was a GABAergic drug. Well, it turns out that they reasoned through all these things that GABAergic drug could do, and maybe some of them it did and some of them it didn't, but it turns out it doesn't work via GABA anyway. It's a sodium channel modulator, right? So, your mechanisms may be wrong, but 2, even if your mechanisms are correct, that doesn't mean that it translates to the real world because of chaos theory. So this is where I always point out that Stahl is our most famous alternative medicine practitioner, is that it's a good way to come up with a hypothesis, maybe a good way to come up with things if you don't have objective randomized controlled trials, but it doesn't mean, because the logic behind it makes sense, that in the real world that your drug is going to work that way. And hence the failure of California rocket fuel. The combination of Effexor and Remeron turned out to, when it was actually subjected to randomized trials, turned out to be no more effective than any other combination of antidepressants. All right. The other big one from the headlines recently, a case control study was published that examined 20 patients with COVID, half of whom received an experimental drug and the other half did not. Rates of intubation were lower in the groups that received the experimental drug. Good initial finding, and then a follow-up. So again, in science, you want to have multiple lines of evidence, right? So they did that. The follow-up study tracked 1,000 outpatients who were given the same drug and found that none of them died from COVID. A third paper, third line of evidence, published showed that the drug inhibits a receptor by which the virus is believed to be transported into cells. Good evidence for multiple points of view that this drug is effective. Should everyone be getting this drug? This has been on the headlines, everyone, if everyone has figured out what this actual example is. So what was wrong with this line of reasoning? Well, to some extent, there's nothing wrong with this line of reasoning. This makes sense. If this were all the evidence there were, we should be going with this. And this is obviously, for those who didn't pick up, the arguments for hydroxychloroquine. And I was personally very excited for hydroxychloroquine earlier on. That, again, the case control study looked really good. That was really exciting. That's actually a pretty good design, a case control study. There were follow-up tracking lots of people. There's an issue with that, though, in that there's no control group. So in a condition that has, somewhere between a 1% and 5% mortality rate, and we have no idea what the infection rate is, the tracking 1,000 people, if you don't have a control group, doesn't really mean anything. But there was a mechanism. So all of this is actually pretty good evidence if you didn't have anything else out there. But the thing that's missing in here is, again, where I talked about you have to look at everything. So this is the case where something could come out and multiple lines of evidence, the arguments seem really, really good, but you need to go back to PubMed and see there are larger studies now that are done in better ways, that are done by the gold standard, the randomized controlled trial. And what refutes good science? Better science. So even though these arguments seemed very legitimate coming forth, that this is a good scientific argument to be made initially, is if there is better studies, if there's more stuff out there, if you look at the broader literature now and the thousands of patients that have been included in randomized controlled trials, and actually the trials had to be stopped because more people were dying in the hydroxychloroquine group than were dying in the control group, we realized that hydroxychloroquine, at least on a mass scale, should not be handed out. Again, there are arguments in terms of niches with that maybe people who are known to have minimal cardiac risk factors and that sort of thing. But in terms of a broad scale thing, there is objective evidence that refutes this earlier evidence, but you have to look for it. So go back and do the PubMed search, go back and do the Google Scholars research. Last ones. So this is one that actually happened while when I was there at Naval Medical Center. Ground speaker came in and talked about a new psychotherapy for post-traumatic stress disorder. He showed several videos with patients before and after treatment, all of them dramatically better. A member of the audience piped up and noted, hey, I've heard about this therapy. It's been reviewed by the National Institutes for Clinical Excellence, that's the British review group, and also by the International Society for Post-Traumatic Stress Studies, actually also by some other agencies. And they all concluded that there is no evidence of benefit, at which the speaker used one of my arguments. He said that the audience member had made the error of appealing to authority and encouraged the audience, therefore, to depend on their own clinical experience and experiments to do this. Was this an example of the Grand Rounds speaker using good scientific evidence, or is there a problem with that means of thinking as well? So the problem here is understanding that other people have done the work before you, and that the National Institutes for Clinical Excellence is a reliable reporter, and their methodology was actually very good. So in terms of doing your own experiment, yes, we always encourage you to experiment, but you need to look at the larger picture. And it's not just an appeal to authority. Again, that we don't toss that idea out that you can never believe anyone again. But you have to understand why they got to their conclusions. And if you understand that groups like this do things in particular ways, that they do take all the steps that I talked about earlier, and they weigh out all the data, and they measure them together, and they put them by Cochrane criteria, that just sort of dismissing that out of hand without breaking down why they make that recommendation, is a mistake. We shouldn't just blow off our professors because, well, I'm not going to listen to authority figures. The authorities got to be authorities for particular reasons. It doesn't mean that we can't challenge them if you know the error of their logic. But to challenge authority does not mean just relying entirely on your own experiment or your own experience. It still involves synthesizing the data and understanding, if you're going to challenge that authority, where was the error in their logic? You can find it, then awesome. But in this case, it's just saying, well, ignore the authority, which is not what these arguments are saying. It's not saying ignore it, but it's saying that you have the right to challenge it. But you have to understand the basics behind it. All right. So bottom line, all of this is a discovery. It's a method that allows thought tools to allow us to work out the universe, to allow us to discover incredible things, to be able to figure out headlines, to figure out things for our patients. It doesn't mean we have to toss everything away. It's still fine to go by clinical guidelines and that sort of thing, but digging deep into them, understanding the challenges, allows us to make better arguments to our patients, allows us to be better providers to them, allows us to be better informed citizens of the world, and may allow us, if you want to become a scientist, if you want to work with these things, really to change the world. So if you're interested in maybe getting into research projects again, I would love for that. But even if you're not, I encourage you, to look at those tools for baloney detection, to look at ways at which critical thinking can break down, to look at every headline that comes out there and look at the real science behind it. A scientifically literate public is one that can change the world. Thank you so much.